Section: Introduction. In this section, we discuss the growing capabilities of large language models, LLMs, and the challenges we face in reliably evaluating their long-form outputs. Recent studies indicate that these models, after being trained on a variety of tasks, can adapt to follow new human instructions. This adaptability makes them promising candidates for automatically rating their own outputs. While human evaluation is essential for understanding model performance, it often suffers from subjectivity, variability among different raters, and high costs associated with extensive assessments. To ensure that our LLM autorators align with human preferences, it is vital to train them using human judgments. However, gathering these judgments can be both expensive and time-consuming. Although we can collect existing evaluations from previous research, we encounter issues like a lack of standardization, varying evaluation criteria, insufficient documentation, and concerns about data privacy and proprietary information. On the other hand, training autorators using model outputs can provide consistency, but it also risks reinforcing biases and inaccuracies, and it may breach the terms of use for proprietary LLM services. To tackle these challenges, we have curated and standardized human evaluations from earlier studies to create Flame, a collection of over 102 quality assessment tasks that includes more than 5.3 million human judgments. Flame covers a wide range of tasks, from evaluating machine translation quality to assessing how well AI assistants follow user instructions. We believe that training on this extensive and varied dataset will help LLM autorators learn strong, generalized patterns of human judgment, reducing the influence of noisy or low-quality evaluations. For transparency and reproducibility, we only use publicly available human evaluation data that comes with permissive licenses from prior studies. To address the difficulties in collecting such data, which often lacks standardization and documentation, we carefully reviewed the related research and consulted with the original authors to clarify any ambiguities, spending several hours on each dataset. We train our LLM autorators through supervised multitask fine-tuning using our curated data. Following the unified task format inspired by T5, we convert all our quality assessment tasks into a text-to-text format, complete with manually crafted task definitions and evaluation instructions. Each training example is structured as an input-target pair, where the input provides task-specific context and the target contains the expected human evaluations. This method allows for effective transfer learning across different tasks, enabling our models to interpret and respond consistently. Our approach aims to develop general-purpose LLM autorators capable of handling various quality assessment tasks. We demonstrate that training an instruction-tuned LLM, specifically PaLM 2-24B, on our Flame collection significantly enhances its ability to generalize across a wide range of tasks, outperforming models like GPT-4, Claude 3, and Llama 3 in many instances. This indicates that our large-scale multitask instruction tuning effectively equips the model with versatile quality assessment skills. Encouraged by these findings, we further explore the benefits of using Flame as a strong foundation for fine-tuning on specific downstream applications, using reward modeling evaluation as a case study. We fine-tune Flame for just 50 steps on a mix of 4 datasets that include human pairwise preference judgments, covering areas like chat, reasoning, and safety. Our resulting Flame ERM24B model shows a notable improvement in performance on Reward Bench, achieving an overall accuracy of 87.8%, up from 86.0%. It stands out as the top-performing generative model trained solely on permissively licensed data, surpassing both GPT-4o125 and GPT-4o. Additionally, we introduce Flame Opt-ERM, a method that optimizes our Flame multitask mixture for targeted reward modeling evaluation. By employing a new fine-tuning technique, we analyze how each dataset affects specific reward bench distributions, allowing us to identify the best proportions of individual datasets in our mixture. After fine-tuning the initial instruction-tuned PaLM 2-24B checkpoint on this optimized mixture for 5,000 steps, we achieve competitive performance on Reward Bench, reaching 87.0% accuracy while using about 25 times fewer training data points compared to Flame. Overall, our Flame variants outperform all popular proprietary LLM as a judge models we evaluated across 8 out of 12 Autorater benchmarks, which include 53 quality assessment tasks like Reward Bench and LLM AgriFact. We also investigate potential biases in our LLM Autoraters, a common concern with LLM as a judge models, and their usefulness in AI development, particularly in identifying high-quality model responses. Our analysis shows that Flame variants exhibit significantly less bias than popular LLM as a judge models on the Cobbler Autorater bias benchmark, demonstrating greater robustness to variations in pairwise ordering, response length, and irrelevant context. Furthermore, we find that Flame effectively re-ranks LLM responses to Python programming prompts in the human eval benchmark, improving the pass rate by 6 to 10% across different settings. In summary, our main contributions include 1. Data collection. We have curated and standardized human evaluations from datasets with permissive licenses, creating a collection of over 100 diverse quality assessment tasks that include more than 5 million human judgments. We plan to make this data publicly available to support future research. 2. LLM Autoraters. We demonstrate the effectiveness of our multitask mixture in training general-purpose LLM Autoraters, Flame, and optimizing them for specific downstream applications, Flame-ERM and Flame-Opt-ERM. Our LLM Autorators outperform all popular proprietary LLM as a judge models we considered across 8 out of 12 evaluation benchmarks. 3. Computationally efficient multitask training. We introduce a novel fine-tuning strategy that optimizes our multitask mixture for targeted distributions, achieving competitive performance with significantly less computational effort. Through our work, we highlight the potential of accessible AI solutions and hope to encourage further research into reusable human evaluations and the development of effective and efficient LLM Autorators. Section Summary. In this section, we address the challenge of reliably evaluating long-form outputs from large language models, LLMs, by introducing Flame, a curated collection of over 5.3 million human judgments across 102 quality assessment tasks. We demonstrate that training LLM Autorators on this standardized dataset significantly enhances their performance in generalizing human evaluation patterns, outperforming existing proprietary models and providing a foundation for future research in effective and efficient LLM evaluation methods. Section: Related Work. In this section, we discuss existing literature related to Autorators and how it connects to our work with Flame. First, we look at automatic evaluation metrics. Traditional metrics like Blue and Rouge evaluate how much the output from a model overlaps with human written references. With the introduction of BERT, new methods have emerged that utilize pre-trained models to assess how similar the distributions of words are or to calculate the probabilities of specific tokens. Some research has focused on statistical techniques to measure how different two text distributions are. Other studies have fine-tuned pre-trained models based on human ratings to develop automatic evaluation metrics for various tasks, such as machine translation, text summarization, question answering, and text simplification. In contrast to these task-specific metrics, Flame is trained on a wide range of detailed quality assessment tasks and can adapt to new tasks during inference. Next, we explore the use of large language models, LLMs, as judges in auto-rating. With the rise of models like ChatGPT, recent studies have employed these models to evaluate their own capabilities across different benchmarks, including Alpaca Eval, MTBench, and WildBench. However, we find that LLM as a judge autorators often show a preference for their own generated responses, displaying biases related to factors like length, order, and preference for certain entities. Our models, on the other hand, are trained on a large and varied set of human evaluations, enabling them to learn unbiased and generalized patterns of human judgment. Unlike LLM as a judge autorators, our models do not evaluate their own outputs, which helps eliminate self-preference bias. We also consider recent efforts to create general-purpose LLM Autoraters. For instance, TigerScore is a model based on Llama 2 that has been trained using error analysis data generated by GPT-4 across several tasks, including summarization and translation. Other similar models include InstructScore, Prometheus, and Prometheus-2. Our approach, however, relies exclusively on open-source human evaluations rather than model outputs. We demonstrate that Flame significantly outperforms Prometheus-2 in our reward bench experiments. Our work is also related to the development of reward models, RMs, that align LLMs with human preferences through reinforcement learning with human feedback, RLHF. In RLHF, human preference data can either train standalone discriminative RMs or be directly integrated into LLMs using algorithms like DPO or SLICHF. While we assess our models as RMs in our reward bench experiments, there are important differences. RMs typically train on pairwise preference data, while our models utilize a variety of task types in a unified format. Additionally, RMs focus on overall preference, whereas our models can be prompted to evaluate specific aspects of model responses, such as safety. We have created the Flame collection by fine-tuning instruction-tuned LLMs on a diverse mixture of standardized human evaluations, which includes 102 tasks and 5.3 million human judgments. This collection is carefully curated to cover a wide range of LLM capabilities. We have manually developed task definitions and evaluation instructions, ensuring that all tasks are formatted consistently in a text-to-text style. When we refer to a task, we mean a specific assignment for the model, which involves presenting a piece of text, such as a machine-generated summary, along with its context, like the original article. We then instruct the model to evaluate certain aspects of the text based on given criteria. Each task has unique definitions and evaluation guidelines, and we can derive different tasks from the same dataset. For example, Help Steer includes human annotations for various attributes of model responses, such as helpfulness and coherence, allowing us to create distinct tasks focused on specific attributes. Moreover, tasks that share similar definitions and evaluation criteria but come from different datasets are treated as separate tasks. Based on this understanding, the Flame collection comprises a total of 102 distinct tasks. In terms of our data collection principles, we prioritize using public, open-source datasets to ensure transparency and reproducibility. We only utilize datasets that are permissively licensed from sources like Hugging Face datasets, TensorFlow datasets, or the original author's GitHub repositories. We exclusively rely on datasets with human-labeled annotations, steering clear of those generated by models like GPT-4 due to potential inaccuracies and legal issues highlighted in recent research. To improve the generalizability of our models, we gather datasets from a wide variety of task types. These include pairwise evaluation, where we compare two responses to determine a preference; pointwise evaluation, which assesses specific attributes of individual responses; classification, where we categorize responses into predefined groups; and open-ended evaluation, which allows for unrestricted answers. Section Summary. In this section, we review existing literature on autorators, highlighting how traditional metrics like BLEU and ROUGE focus on lexical overlap, while newer methods leverage pre-trained models for more nuanced evaluations. We emphasize that our Flame model, trained on a diverse set of human evaluations across 102 distinct tasks, avoids biases seen in LLM as a judge autorators and outperforms other general-purpose models by relying solely on open-source human annotations. Section: Various LLM capabilities. In this section, we choose datasets from existing literature that evaluate various capabilities of large language models, LLMs, such as factual accuracy, safety, reasoning, following instructions, generating long-form content, creativity, attribution, and coding skills. We have compiled a comprehensive collection of 5.3 million data points across 102 training tasks, with an additional 53 tasks set aside for evaluation. The list of datasets we used can be found in the appendix. Our data collection focuses on the essential capabilities of modern LLMs, which we outline below. To assess the quality of LLM responses, we utilize several datasets that measure attributes like helpfulness, coherence, fluency, creativity, complexity, and verbosity. These datasets include summary comparisons, LMSYS chatbot arena conversations, HHR-LHF helpfulness, WebGPT, SumEval, News Summary Evaluation, SHP, Beaver Tails helpfulness, Seahorse, Help Steer, and others. For evaluating how well LLMs follow instructions, we include datasets such as Genie, Instrusum, and Risum. Recognizing the growing need to measure inaccuracies in LLM outputs, we incorporate datasets that evaluate the factual correctness of responses and their grounding in source documents. These datasets include XSum hallucination, QAGS, Wikibio hallucination, Frank, FactScore, Vitamin C, HaluEval, Q-squared, FaithDial, DialFact, Begin, and MNLI, among others. For mathematical reasoning, we create datasets that help Flame distinguish between correct and incorrect solutions to math problems. We use PRM800K to gather examples of human solutions versus incorrect LLM-generated solutions, as well as pairs of correct and incorrect LLM-generated solutions. In addition to evaluating natural language, we also train Flame to assess code. We use datasets like code contests, CommitPack, and Coffee to create pairs of correct and buggy programs in response to coding challenges or GitHub issues. The model learns to identify the correct program or fix from each pair, covering popular programming languages such as Python, JavaScript, Java, C++, Go, and Rust. Ensuring the safety of AI assistants for public use is increasingly vital. To support safety evaluations, we train Flame to recognize more helpful and harmless responses. Our training data includes tasks from sources like HHR-LHF harmlessness, HHR-LHF red teaming, and Beaver Tails QA classification and harmlessness. To maintain the instruction following abilities of our models, we also include instruction tuning data from datasets that feature human-written responses, such as Lima, PRM800K if, and TULU2. After selecting our training datasets, we standardize them into a unified text-to-text format. This preprocessing typically takes about 3 to 4 hours per dataset and involves several key steps. 1. We conduct a thorough review of the related research and consult with the original authors to clarify any ambiguities. 2. We gather all relevant data files from sources like Hugging Face datasets, TensorFlow datasets, or GitHub repositories. 3. We identify and extract specific data fields that contain quality assessments made by human annotators. 4. We create detailed task definitions and evaluation instructions for each quality assessment task, ensuring consistency and standardization while adhering to the original evaluation criteria. 5. Finally, we reformat all tasks into a text-to-text format, where task definitions, evaluation instructions, and desired output fields are organized under an instructions block, while input and target field values are placed under context and evaluation blocks, respectively. This flexible format allows us to adapt to a wide range of quality assessment tasks. We then use our extensive and diverse mixture of quality assessment tasks to train general-purpose LLM Autoraters, which can be prompted during inference to perform various tasks. We develop 3 model variants: Flame, which is trained with examples proportional mixture weights; Flame-ERM, which starts with Flame and is slightly fine-tuned on a balanced mixture of 4 pairwise evaluation datasets covering chat, reasoning, and safety; and Flame-Opt-ERM, which is trained with reward modeling optimized mixture weights using a tailpatch fine-tuning strategy. Section Summary. In this section, we detail our comprehensive dataset collection of 5.3 million data points designed to evaluate various capabilities of large language models, LLMs, including factuality, reasoning, coding, and safety. We also describe our unified task format for training our model variants, Flame, Flame-ERM, and Flame-Opt-ERM, which are designed to assess and enhance the quality of LLM responses across multiple tasks. Section: Training General-Purpose LLM Autorators, Flame. In this section, we describe our approach to training general-purpose language model autorators, which we refer to as Flame. We begin with a baseline method that involves supervised multitask training, where we train an instruction-tuned PaLM 2 to 24B model on a mixture of tasks for a set number of 30,000 training steps. To ensure a balanced representation of tasks, we use mixture weights that are proportional to the number of examples, with a maximum limit of 65,536 per task to prevent oversampling from larger datasets. Our Flame model shows a significant improvement in its ability to generalize across a variety of tasks that were not included in the training, outperforming models such as GPT-4, Claude 3, and Llama 3 on many of these tasks. This supports our idea that large-scale multitask instruction tuning can effectively provide the model with the ability to assess quality in a general sense. However, we also discover that this method is not the best for specialized applications, such as reward modeling evaluation, which leads us to develop targeted approaches for specific downstream tasks. Next, we focus on fine-tuning Flame for reward modeling evaluation, which we call Flame-ERM. Building on our earlier findings, we explore how Flame can serve as a strong foundation for further fine-tuning on specific applications. For our case study, we fine-tune Flame on a mixture of 4 pairwise evaluation datasets, which include Help Steer, PRM800K, CommitPack, and Hydrogen Hydride RLHF Harmlessness, all mixed equally. Since Flame has already been trained on these datasets, we only need to fine-tune it for 50 steps. The resulting Flame-ERM model shows a notable increase in the overall score on Reward Bench, improving from 86.0% to 87.8% accuracy. Impressively, Flame-ERM 24B becomes the top-performing generative model trained solely on permissively licensed data, surpassing both GPT-4o125 and GPT-4o. We then turn our attention to optimizing the Flame multitask mixture for reward modeling evaluation, which we call Flame-Opt-ERM. While our initial Flame mixture performs well across various tasks, we find that it requires extensive training to achieve strong results on certain specialized applications, such as Reward Bench. We believe this is due to suboptimal mixture weights that do not adequately sample beneficial tasks during training. To tackle this issue, we introduce a new strategy called tail patch ablation, which helps us analyze how each dataset impacts targeted distributions. This allows us to determine the best proportions for each dataset in our multitask mixture, optimizing all mixing weight parameters simultaneously. By fine-tuning the initial instruction-tuned PaLM 2 to 24B model on this optimized mixture for just 5,000 steps, we achieve competitive performance on Reward Bench, reaching 87.0%, while using about 25 times fewer training data points compared to our baseline Flame approach. We note that our aim is not to achieve the highest possible results on Reward Bench but to show how we can optimize our multitask mixture for specific distributions. We also observe that additional training or fine-tuning, as done for Flame-ERM, can further enhance our Reward Bench performance, although we did not submit these Flame-Opt-ERM results to the official leaderboard. Furthermore, Flame-Opt-ERM demonstrates strong performance across other held-out tasks, indicating that we have not overfitted to Reward Bench and that Flame-Opt-ERM is broadly applicable to various tasks. To determine the best tasks for our training mixture, we recognize that setting the right mixing weight for each task is challenging due to the large number of tasks involved. Therefore, we assess the impact of each task on targeted distributions and use this information to assign weights. We start with a checkpoint that has been partially trained on our initial mixture, which shows decent but not optimal performance across Reward Bench categories. We then conduct a brief fine-tuning phase, referred to as tail patch, on each individual training task, limited to 3,000 training steps. We believe that training on beneficial tasks will help us achieve better performance. This process is done once for each downstream application and can be performed with smaller models to reduce computational costs. After completing the tail patch training, we evaluate how helpful each training task is for each category of reward bench using a rating system. We categorize tasks into 7 bundles based on their ratings, which range from significantly helpful to harmful. We assign fixed mixing weights for each bundle, with higher weights for generally helpful tasks and lower weights for others. A task can belong to multiple bundles, and its final weight is the sum of the weights from all bundles it is part of. For instance, if a task is generally helpful and also beneficial for 2 specific categories, its contribution to the final mixture is calculated accordingly. We also prioritize the top 2 most helpful tasks in 3 categories that performed poorly, assigning them a higher fixed weight. These weight values were initially based on our intuition and were not extensively fine-tuned. Finally, we initialize Flame Opt-Erm with the instruction-tuned POM2 to 24B and then fine-tune it using our re-weighted multitask mixture. Section Summary. In this section, we describe our training of the Flame model using supervised multitask instruction tuning, which significantly enhances its generalization capabilities across various tasks, outperforming models like GPT-4. We then fine-tune Flame for reward modeling evaluation, creating Flame-Erm, which improves accuracy and demonstrates the effectiveness of our optimized multitask mixture approach, ultimately leading to Flame Opt-RM that balances training weights for better performance on targeted applications. Section: Training Details. In this section, we outline the training details for our models, Flame and Flame Opt-Erm, which we initialize using the POM2 to 24B model that has been instruction-tuned on the Flan collection. We train Flame for 30,000 steps and Flame Opt-Erm for 5,000 steps. After this, we fine-tune Flame for an additional 50 steps to develop Flame-Erm. Our training process utilizes T5X with the Atom Optimizer, setting the learning rate at 0.0001 and the dropout rate at 0.05. For training, we employ 256 cloud TPU chips with a batch size of 32 for Flame, while Flame-Erm and Flame Opt-Erm use 128 cloud TPU chips with a batch size of 8. Next, we present our main experiments, where we compare Flame against several well-known LLM as a judge Autorators. We use an evaluation suite that consists of 12 Autorator benchmarks, including 1 held-in and 11 held-out benchmarks, which cover a total of 53 quality assessment tasks. Our findings indicate that our Flame variants, which are trained solely on permissively licensed data, outperform LLMs trained on proprietary data, such as GPT-4 and Claude 3, in 8 out of the 12 benchmarks. To evaluate the general quality assessment capabilities of Flame, we use a diverse set of tasks, both held in and held out. We format each task into a unified text-to-text format and prompt our models accordingly. For benchmarks that have multiple categories, like Reward Bench and LLM Agrifact, we maintain consistent prompt instructions across these categories. To manage model API costs, we randomly sample 256 examples for each evaluation task, except for Reward Bench, where we use the complete evaluation sets. For held-in evaluations, we assess Flame's performance on various aspects such as helpfulness, correctness, coherence, complexity, and verbosity using the Help Steer validation set. In terms of held-out evaluations, we focus on Reward Bench, a well-known benchmark for evaluating reward models, which emphasizes their capabilities and safety. This benchmark involves tasks where reward models must choose the better response between 2 options based on a prompt, and it includes 4 main categories: chat, chat hard, reasoning, math and coding, and safety, comprising 23 individual datasets. We also evaluate Flame using LLM Agrifact, which measures the grounding capabilities of Autorators. In this benchmark, given a reference document and a claim, the Autorator determines if the claim is fully supported by the document. This comprehensive benchmark includes 10 attribution datasets used in recent studies on LLM factuality. In addition to Reward Bench and LLM Agrifact, we assess Flame on a variety of other held-out benchmarks that involve pairwise comparisons and pointwise evaluations. These include summary comparisons, helpful, honest, and harmless alignment, alpaca farm, paraphrase evaluation, sequence continuation preference, poem preference, literary translation comparisons, long-form QA evaluation, and text continuation preference. Importantly, none of the tasks in these benchmarks were part of our training data. For our evaluations, we compare several popular LLM as a judge models as baselines, including Llama 3 to 70B Instruct, Mixtral with 8 times 7 billion parameters, Claude 3 Opus, GPT 3.5 Turbo 0125, GPT 40125, and OpenAI's current flagship model, GPT 4o. We also align our results with several models on the official reward bench leaderboard, particularly Gemini 1.5 Pro, Prometheus with 2 times 7 billion parameters, and NVIDIA's NEMOTRON4-340B reward and Llama 3 to 70B Steer LM-ERM. We evaluate all three of our Flame variants, Flame, Flame-ERM, and Flame-Opt-ERM, as detailed in previous sections. Additionally, we include the initial instruction-tuned PaLM 2 to 24B checkpoint, which has not been trained on our Flame data, to help us understand the effects of instruction tuning versus Flame training. Finally, we present our main results across all evaluation benchmarks, with specific results for Reward Bench and LLM AgriFact shown in their respective tables. Section Summary. In this section, we detail our training process for the Flame models, initializing with the PaLM 2 to 24B model and training on cloud TPU chips with specific batch sizes and learning rates. We then present our evaluation of Flame against various LLM as a judge models across multiple benchmarks, demonstrating that our models, trained on permissively licensed data, outperform proprietary models on several quality assessment tasks. Section. Flame variants outperform all LLM as a judge baselines on 8 out of 12 benchmarks. In this section, we present our findings regarding the performance of Flame variants compared to other models. Our results indicate that Flame variants, which were trained exclusively on datasets with permissive licenses, show strong performance across various evaluation benchmarks. Notably, we find that our models outperform all leading LLM as a judge models that were trained on proprietary data in 8 out of 12 benchmarks. For instance, in the Contour Search benchmark, our model scored 69.9, significantly higher than the 57.5 achieved by GPT-4o and GPT 3.5 TURB00125. Similarly, in RankGen, we scored 69.5 compared to 66.0 for GPT-4o, and in Alpaca Farm, we achieved 58.2 against 55.5 for GPT 3.5 TURB00125. Our models also excelled in Sum Feedback and Reward Bench, scoring 53.1 and 87.8 respectively, surpassing the scores of competing models. While we achieved the best performance on Help Steer, scoring 48.4 compared to 41.3 for Claude 3 Opus, we did find that Flame variants did not perform as well as proprietary models on some benchmarks, such as HHH, LitTrans, and LFQA EVA. This suggests that those proprietary models may have been specifically optimized for those tasks. Interestingly, we observed that GPT-40125 outperformed GPT-4o in 6 out of 12 benchmarks, including Reward Bench, even though GPT-4o had a higher rank on the official LMSYS leaderboard. Overall, our results highlight the significant improvements that Flame provides over the initial instruction-tuned PaLM 2 to 24B across nearly all benchmarks, demonstrating its strong generalization capabilities and effectiveness as a versatile LLM autorator. We also found that Flame variants rank among the top generative models on the official Reward Bench leaderboard, performing well across all categories, including chat, hard, safety, and reasoning. Specifically, Flame-ERM 24B achieved an impressive overall score of 87.8%, outperforming both GPT-40125 and GPT-4o. As of July 15, 2024, Flame ERM24B is ranked second among generative models and sixth overall on the reward bench leaderboard. However, we did identify some issues related to length and token bias during our evaluations, which we discuss further in the appendix. Additionally, we present our results on LLM AgriFact, where we categorized our findings into 4 common use cases: fact verification of LLM-generated responses, evaluating the correctness of Wikipedia claims, assessing the faithfulness of summaries, and evaluating long-form answers to questions. In 3 out of these 4 categories, Flame variants outperformed all other models, with Flame 24B achieving the highest overall performance score of 81.1, compared to 80.6 for the next best model, GPT-40125. However, in the long-form QA evaluation, our best model, Flame Opt-ERM, did not perform as well as GPT-40125. Finally, we shift our focus to analyze some intriguing aspects of our models. Instead of concentrating on factors like model size, and data quality, which have been widely studied in multitask learning, we explore potential biases present in our LLM Autoraters. We also demonstrate how Flame can be useful for AI development, such as generating high-quality responses. Section Summary. In this section, we demonstrate that Flame variants outperform all state-of-the-art LLM as a judge models on 8 out of 12 benchmarks, achieving significant gains over previous models despite being trained on permissively licensed datasets. Additionally, we highlight Flame's strong performance on the reward bench leaderboard and its superior results in fact verification and summarization tasks, while also addressing potential biases in our models. Section: Autorater Bias Analysis. In this section, we analyze the bias present in LLM as a judge autorators, which is a common concern. We evaluate different Flame variants using the Cobbler Autorater Bias benchmark. Our findings indicate that our models show significantly less bias compared to other well-known LLM as a judge autorators. Cobbler assesses 6 types of biases in LLM autorators. 1. Order. This checks if the autorator favors responses based on their position. 2. Compassion. This examines whether the autorator's judgment changes when the actual name of the response-generating model, like GPT-4, is used instead of generic names like Model A. 3. Length. This looks at whether the autorator prefers longer or shorter responses. 4. Egocentric. This determines if the autorator favors outputs generated by itself. 5. Bandwagon. This assesses if the autorator is influenced by statements like 90% of people prefer response A. 6. Attention. This checks if the autorator gets distracted by irrelevant information, such as response A is about cats. We utilize the original pairs of prompts and responses and reformat them into our unified Flame structure. We then compare the performance of Flame variants against other LLM as a judge autorators, including GPT-4. Our results reveal that Flame variants have a significantly lower average bias of 0.13, compared to 0.31 for GPT-4, indicating that lower values are better. Flame performs either significantly better or on par with GPT-4 across all 6 bias categories. These results highlight Flame's effectiveness as a strong and dependable autorator. Next, we investigate how our LLM autorators can be used to select the best outputs from multiple responses, a technique known as best of N sampling. We apply Flame for re-ranking and evaluate its effect on code generation performance using the Human Eval Python programming benchmark. In our experiments, we re-rank 10 code samples generated by 3 models: OpenAI's DaVinci 002, INCODER6B, and CodeGen 16B, using a round-robin method, and then measure the performance of the top-ranked code sample. The results show that Flame significantly enhances pass-at-1 accuracy for all 3 models. Specifically, Flame boosts CodeGen 16B's pass-at-1 from 21.2 to 31.1, which nearly closes 40% of the gap to the Oracle ranker, which has a score of 46.9.